I have made a buffer amplifier like this with 4 BF240 in parallel. These ferrite beads are to prevent microwave oscillations. They give about 8 ohms on 10 MHz, and on 150 MHz they are a 50 ohm loss, regardless what is connected on the other side, I think. I moved the 470 ohm load to this place and this capacitor to couple it to the resonator and this resistor to give a voltage for the bases. The current is 15 milliamps. And the impedance here is very low, so I put the 50 ohm resistor here to have 50 ohms impedance on the output. At the modest signal level, the red trace is what I see at the limiter output. So this is much better than before, although it's not as good as when there is no buffer amplifier. As it turns out, the 4x BF240 amplifier is no good. The first run, the red trace here looked reasonably promising, and I repeated it with the same settings and got even better, like here. But then I have tried at higher signal levels. 5 dBm is very low. 10 dBm, that's the brown trace, it's up here. And that's not promising at all. What I have to compare with is this dark green trace down here, which was what I had without this buffer amplifier. I am looking at the feedback output from the limiter amplifier, and there is a dummy load on the output from the BF240 amplifier. Then, when I increase the power up to 14 dBm, I get this green trace, nearly as much noise as with the crystal. And then finally, I have removed the dummy load on the output, and that gives about the same as the crystal. But there is no crystal there now, so this is a serious degradation. This means that the load from the input of this 4x BF240 amplifier creates noise that is seen by the limiter amplifier and would feed back to the input and make a noisy oscillator. So I have to scrap this and find out some other way of solving the problem. I have made some small changes to the amplitude limiter, putting ferrite beads here rather than 50 ohm resistors, because that's what they are, about 150 megahertz. But at lower frequencies they are a very small inductance. And then I changed the number of turns on this transformer, so now the impedance here is 50 ohms. These two parallel resistors are transformed to 50 ohms at this point, and when this is tuned for resonance it is almost zero impedance. I have made several measurements on the same thing, and the Allen deviation becomes very similar. The brown trace is with lower power, and that is the same. And I don't know exactly why this one, the third measurement, sticks out at 200 seconds or even 100, but everything is very much the same up to 30 seconds. The reason why I made several measurements will be obvious when I look at the phase difference. I made several measurements. They are listed here in chronological order. The first one, the dark green, there the phase difference drifts with time in a linear fashion. And the second one, about 3 hours after the first, it was started fairly soon after the first was finished. That is drifting, but with about half the slope. The third one, several hours after the second one was finished, it still has a slope.
And the fourth one, long after the third one, is still slopes. And I don't think that is temperature. I think that is some glue that I was using is slowly hardening and causing some slow shift by a varying dielectric constant perhaps. When I zoom into the measurement, I can see that the last one, which was at lower power, is drifting and noisy, low-frequency noise for the first 3,300 seconds, and then it becomes much nicer. And I don't know the reason for this, because the system has been running. Well, the tiny PFE was not working for a while before I started, so this may be caused by the tiny PFA. Anyway, what I am about, the magenta trace here, that is the crystal noise, which is very much higher than the noise I have from the limiter and amplifiers, at least when looking in this time span. I have removed the selective amplifier and replaced it by a BNC female-to-female adapter. And then immediately started measurement, and then you can see the trace looks very bad because the tiny PFE has been idle for maybe 1 hour or something of that order. And looking at the phase difference, that is what I see. So I have to wait for this to stabilize before trying to see what the performance is of my test system right now. After 25 minutes, the trace is fairly flat. Now Allen deviation comes in here, and it goes fairly fast until it reaches this interesting point. I have zoomed in on the interesting region, and here comes the new measurement of nothing, and it looks very similar to the old one. With nothing as the device under test, the bright green trace here, I see that the system is now less stable than what it was when I made the blue one, but still it's far below what I can see from my selective amplifier. And when I look at the phase difference versus time, I see this drift with time, and the variations, the undulations on the track are bigger than they are on the blue trace. So something is not quite as it should be. I have added a second limiting amplifier here. It's identical to this one, except that I had to add these RC links between base and emitter to prevent oscillations at something like 1 gigahertz or 800 megahertz. I didn't take down exact frequency. As it turns out, the performance has degraded a little. The green trace here is what I had in the first limiter when there was only one limiter. The blue trace is the same when I added the second limiter. And the second limiter is the red trace, and it is not quite as good as the blue one. When I look at the phase difference versus time, this is what I see. The first limiter had this frequency drift, but it was a very smooth curve. When I zoom into the graph, I find that the magenta trace, the ugly one here, that is the crystal filter. And then the dark green here, that was the first limiter, the nice measurement. And the red trace, which is oscillating, and then not so much. That was the new limiter on the output side. And the blue trace, when I repeat that measurement, which was the green trace, but now it looks like this. And it is more noisy than it was before. But compared to the crystal filter, all the others are very good.
I have removed the 470 ohm resistor that I had on this transformer, because I have added load on the secondary side, these connected. So the load from this corresponds to about those 470 ohms that I have removed here.
Removing that resistor has restored the correct voltage on 4 turns on that transformer on the other side where the 470 ohm resistor was. And that is at an input signal corresponding to 10 dBm into the crystal filter input. So this is an old measurement, and it's the green trace comes here. And then red and blue are the new outputs from the limiter, the output limiter and the feedback limiter, and they are very similar. And what I saw recently at 14 dBm, before I made that change, then I saw this difference between the output limiter and the feedback limiter, red and blue. But a measurement without the second limiter was more interesting here, the green trace. I don't know why that is, but I can compare here what I now have and this exceptionally lucky measurement. And that result, the green trace, was with this time function. That was when it was drifting very rapidly. Anyway, these slow variations on the phase shift are not important because I'm interested in the phase modulation of the oscillator and not the long time stability.
I have added a power amplifier here. It's the same amplifier I used earlier, but now it's after the limiting stage. And the output power now is 19 dBm.
Here is the Allen deviation of the phase shift from input to output of the amplifier without the crystal involved. So the top trace here, that is with the crystal filter. And down here is the amplifier. At 10 seconds, these two traces are from the power amplifier and the other ones are from the limiting output, one or the other. And the difference here, I can see there is some noise from the power amplifier and also at short times, 1 second. So this could be a problem, adding phase noise from the buffer amplifier. But at longer times, it doesn't matter. Here are the two outputs. The two upper traces are from the 19 dBm output connector, while the green trace is from the feedback. And you can see there is a difference. It's about a ratio of 5 to 4. The separation is from 2, 3, 4, 5 to 4. That's 25%. And that's in amplitude, so it's about 2 decibels, I think. Anyway, the green trace that is in the feedback loop, their phase shifts give a frequency shift directly. While the buffer amplifier, when it adds phase shifts, if it happens slowly, let's say at 10 seconds, that will not create many sidebands, very weak, because that is phase modulation, while from the feedback port it gives frequency modulation. But I can see at below 1 second there is still a difference between the traces, so it is possible that the buffer amplifier is harmful at offsets about 1 Hz from the carrier. I will look at that, and if that is the case, I will have to modify the buffer amplifier. Here we can see the phase shift through the amplifier will determine the frequency that it gives as an oscillator. And from the feedback port you can see this is what we have seen, some frequency drift over long times, but this fairly rapid fluctuations, that is the phase noise. And from the output from the power amplifier we can see slow phase shifts, completely harmless, and maybe a little bit more of these short-term variations, but this is hard to see. I can zoom into the graph and pick a small region here. And here one can see that the blue trace looks more noisy at short times. It is now, each division is 2 seconds. While the red trace, which is exactly the same according to the Allen graph, it doesn't differ much from the green trace. So I don't know what to do about these things. I think it will be better visible in the frequency domain. I have connected the feedback cable internally in the box from this connector to that, to avoid the BNC connectors, which sometimes presents problems. And I have replaced these 2 SDR IP units by this unit, a PN2060. And here is phase noise with Linrad and my 2-channel direct conversion receiver and the PN2060. And they agree almost. There are some little differences. So for example at 1 Hz I see here 121.9, and if I look in Linrad I see at 1 Hz here minus 124. 0.1 Hz I see minus 84, and 0.1 Hz minus 84.2. There is full agreement. At 100 Hz here it is minus 160, just starting to go up. In Linrad at 100 Hz it is also minus 160, but the noise floor seems flat. It starts to go up maybe somewhere around 40 Hz. It's hard to judge because here I have problems. And at the very low end, 0.01 Hz, there are differences. For some reason here, the phase has become incorrect because the bright gray trace is above, means the imaginary part is stronger than the real part, so there is some problem with phase shifts. I don't see that in Linrad, but it looks peculiar because the at 0.01 Hz it is a bit blue here, which means that the correlated part is negative. That's also an error in the phase somehow. But it's different here and here. The imaginary part is well below the real part, but not as much as higher up in frequency. I don't know what it all means. Probably that I should not worry about 0.01 Hertz, that is 100 seconds. But at, let's say, 0.2 or 0.3 Hertz, it looks like both measurements agree reasonably well. And at 10 Hertz, I see in Linrad minus 151, and in the PN2060 I see at 10 Hertz minus 145.5. So there is some noise in this region that originates in the PN2060, but otherwise agreement is good. When I look in the linear frequency scale with Linrad, I can estimate what I think the noise at 0.01 Hertz is, and I would say minus 41 dBc per Hertz. And 0.02 Hertz, here minus 54. 0.05 minus 71.5. And I continue and take down the data and plot on paper. The amplitude noise is very low. Down here the imaginary part is equally strong as the real part. So the noise is below what the white traces indicate here. Not very far below, because there is much more white than blue here. But at 0.1 Hertz, I clearly see amplitude noise. And looking at the correlation between amplitude modulation and phase modulation, I see they are independent from about 0.03 Hertz up to about 0.3 Hertz. At very low, 0.02, here is a signal of some kind, and also here. So there are problems very close to the carrier for reasons I don't know. And above 1 Hertz offset, it seems that there is a correlation between phase noise and amplitude noise. And it is the imaginary part, means the yellow trace, so the modulations are phase shifted by about 90 degrees. By resizing windows, I can make a decade equal in size in Linrad and in the PN2060. So here I have the fractions within the decade. And I set the vertical scale for 5 divisions to be 50 millimeters. So there will be 1 millimeter for 1 decibel. The lowest values are too uncertain. I don't think I can judge what this means, but at 0.03 Hertz, it would be where the mouse is. That's about minus 62. And 0.04 would be where the mouse is, minus 67. I have connected the same signal to all 4 ports of the PN2060. And here is a power splitter. It says 40 megahertz, but it's perfectly okay also at 10 megahertz. Here is the internal noise of the PN2060 from feeding all 4 inputs with the same signal. And here we can see it's piecewise linear within about 1 decibel, between 10 and 1 kilohertz, even more accurately between 1 kilohertz and 100 hertz. And then here, all the way deep, here the noise level is rather uncertain, but it is very low, so it doesn't matter. I can take it as something like that. Here is the result. On this graph is plotted since long ago the rubidium source, an LPRO 101,
And then the red dots, that is my vent cell 501-25420. And the green trace, that is the measurement I just made on the new oscillator. The measurements with the PN2060 and my Linrad system agree perfectly well over from here to this point. And here the LPRO gives a reading that is too noisy. And then above about 100 Hz they agree again. And then the red curve here, that is the PN2060 with the same signal on all 4 ports. And it's obvious that it's the noise from here that contributes. At this point, the 2 noise sources are equal, so I should expect to see 3 decibels above here. And I see something like 5 decibels. But more interesting is at this point, 40 Hz, I see a level that is significantly below the internal noise of the PN2060. And I cannot explain why. Maybe something, pickup from the USB or something else has changed. One obvious thing is that the flat noise floor at minus 160 decibels, it is much higher than expected. I have seen before minus 185 approximately. I will have to look into that. And then I see here, this oscillator I now have is more noisy than the vent cell, around 0.1 Hz. Maybe that's the power amplifier of my oscillator. I could see that there was some problem at about 1 second and up to about 10 seconds in the Allen graph. But here, where I had a problem with much higher noise, here the curve looks fine. It's a straight line now. I have disconnected the power amplifier. So I take the output directly from the limiter, and the impedance at that point is 50 ohms. And my oscillator now at 0.1 Hz here is at minus 84.3 or something like that dBc per Hertz, while the vent cell was, I measured minus 88, but I find the line is more like 89. Removing the buffer amplifier at the output makes no difference at all. I see now minus 84.3, so the output amplifier did not affect that at all. But it seems that the wide noise floor here is a little bit lower, so I will leave the output amplifier disconnected while investigating the wideband noise floor. I have now connected the vent cell oscillator to check that old measurement. And as it turns out, now I get a different result. Here, 83.5. And then 120 at 1 Hertz. So what I see with the vent cell are these points. And they agree with my measurements on my own oscillator, but the old measurement from nerds101 2 months ago about differs by as much as 5 decibels. And the line I draw between these points was even a little bit below that. I cannot explain this. I'm really confused. I have not changed anything with the vent cell oscillator. It's fed from the same power supply. It's still in that cardboard box with the same big capacitor filtering it. So I'm surprised. I don't know. I haven't changed anything with the hardware as far as I know. I have found the error. While I was using the tiny PFA to measure phase shifts through the amplifier, I was using my channel 2 oscillator as the signal. And then when I connected it back to my 2-channel receiver and also to the PN2060, the phase locking jumped out of lock. So to make it connect faster, I turned this knob to the same position as this one has. It means I have 2 kilo ohms in the RC time constant, while it should be like it is now. Then it is 100 kilo ohms. So it is about 50 times longer time constant as it should be. While I had it in this position, the time constant is not very long, so I had correlated noise from the rubidium source in both oscillators, and that's why I saw a higher noise level, and also that the imaginary part was higher than the real part. So this was operator mistake. The computer has crashed. It could be because the PN2060 is saving data and suddenly memory is full or something. Anyway, I have still the result on screen. So at 1 Hertz I see minus 122, and at 0.1 Hertz, where I had the problem before, I saw only 83 and I expected 88. Now I have 88.9 at 0.1 Hertz. And looking in Linrad at 0.1 Hertz, here it looks like minus 88. And here the imaginary part is relatively close. It's only 5 decibels. So there is a contribution of random noise in the real part also. I have taken down what I can read from the screen and we put it on paper. So the green marks here are my new measurements, and they come very close to the old measurements of the Wenzel oscillator. About 1.5 decibel below in this region, maybe 2. This particular point, they have the same value. That's where the curve bends. And then at higher offsets, 1 Hertz, there is a significant difference between my oscillator and the Wenzel. And then here, the red rectangles, they are the measurements with the PN4060. They agree with the Linrad measurements, and I have taken the average of them in this region. But above about 1 Hertz, the contribution from the noise of the PN2060 lifts the noise a little bit, and it's worst at about 10 Hertz. And here, this line is the measured noise of the PN2060 itself. And something is wrong with that, because I measure better than this line at 30 Hertz offset. And that is like it was before. And I don't know the reason for it. Anyway, now I'm satisfied with the close range performance of this oscillator. I have changed the transformation ratio here from 12 and 18 to 30 and 30, which means that the impedance that this amplifier looks into is a little bit higher. And in turn that means that I have lost a little performance at very close range, about 1 decibel at 1 Hertz. But I have gained a significant improvement in the noise floor at wide separations. Here I'm looking at the amplitude noise.
with my 2-channel direct conversion receiver and with the PN2060 and its software. And I see various funny things here. For example, at 10 kHz, the PN2060 tells me that the noise floor is minus 176. And if I look in Linrad, I can see that 10 kHz, it is here. That is approximately the maximum frequency that works with this setup, because I have this bending here, which has to do with internal filters in Linrad. So I can trust this measurement up to about 8 kHz. And at 8 kHz I can read minus 176. And I have here minus 176 at 10 kHz, but it is flat. So probably really it is flat. This bending here is an artifact which I should compensate for, and then I would see a flat floor here. Then at halfway between 1 and 10 kHz, here there is a sharp increase in the floor noise. But if I look in Linrad, I don't see that, but I do see all these spurs that are related to overtones of the audio frequency in the direct conversion. Maybe this thing goes into the PN2060, probably so. Anyway, what is more intriguing is this large peak here. That suggests there is a problem. I will try to investigate that. I have added a bandpass filter with a bandwidth of 650 Hz. That filter produces noise, not very much. There are about 25 crystals in it, and they operate with very little power in each one. But still they produce noise, and we can see that best near the corner frequency, here somewhere. Before it was down here, and now it is up by maybe 6 decibels or so. Out here, the noise is the same, and notably it's below the uncorrelated noise with the same distance here and here. So what I see here is probably a defect of my measurement system. The PN2060, that's different. This is without the filter, and here is with the filter. And the filter reasonably produces noise here. So it lifts the noise floor a little bit. But for some reason, above, is it 50 kHz? It doesn't produce any noise at all. It looks very odd, I think. And this is amplitude noise. I will now look the same way at phase noise. Here is the phase noise after about 7 hours. The narrow filter with crystals is still connected. And here we can see similar results with Linrad and with the PN2060. At 1 kHz, 170 dBc per Hertz. Here, 170. And then at about 3 kHz, Linrad doesn't work anymore. Here we have correlated noise of the wrong sign. That's an artifact of the system. But the level is minus 185. And in PN2060, there are structures and a noise below minus 180. There is a peak here of some unknown. Most probably the noise floor after the filter is well below, but this is the properties of the measurement system, as well as here. I have removed the bandpass filter, so here is the phase noise of my experimental oscillator. And we can compare it with the result when the filter was in place. Look here. That's the noise floor of the test system. And 10 dB higher is the noise of my oscillator. And there is a structure here. And I can compare with the Linrad result. You see a flat noise floor here around 5 kHz all the way to about 1 kHz and up to 8. And then when it goes down, it's because of this filter characteristics. So the flat noise floor between 1 and 10 kHz is here, minus 176. From 1 to 10, it says at 10 kHz, 175.9, and 1 kHz, 174.1. So they are very close to each other. So I can trust that is the noise I have. It's interesting to compare the phase noise, which we have here, to the amplitude noise, which is here. This structure here is evidently mainly amplitude noise, but it has a component of phase noise as well at the same place. And the amplitude noise is lower than the phase noise, above 100 kHz. So I will look at the very wide noise to see what is the reason for this. Seems that there is AC voltage in the range 20 to 100 kHz on the supply rail to some amplifier. And that noise at high audio frequencies, 20 to 80 kHz, is generated somehow by the amplifiers in the box. Because I don't think they can come from the power supply. The best way to study wide-range sideband noise is to use a notch filter. Here I have first a selective load. It's a notch in series with a 50 ohm resistor. It presents 50 ohms at 10 MHz, but otherwise it just routes the signal through these two connectors without any load. Then there is a quarter wave cable, and after that is a notch at 10 MHz. This presents a zero or close to zero impedance at 10 MHz, and due to the quarter wave cable that becomes an infinite impedance. That means that the oscillator looks into 50 ohms at 10 MHz. And then the signal here goes into a preamplifier and then a Perseus SDR. And here is what I see. There are obviously strong signals, that means modulation, at both sides of the carrier. The carrier is here, and I could attenuate it more, but that doesn't make any difference because I see what I want to look at. I will try to decouple the supply voltage just by holding an electrolytic capacitor like that. And as you can see, it made a big difference. I can try at the other end of the supply cable. It is a screened cable, and it goes to these electrolytic capacitors. And when I try to decouple here, there is no difference at all. So I have low frequency pickup in this screened cable, and I will place this
decoupling capacitor inside the box.
By the way, the reason why there is an asymmetry between the low frequency side and the high frequency side is that there is AM as well as phase modulation by this AC voltage that is picked up by the cable. But AM sidebands are in phase while phase noise sidebands are out of phase. So they add with the negative here and with the positive here. So this is all according to what one would expect. And then there are some structures here that are spurious resonances from the notch filter. Here I have added the 650 Hz filter. And as you can see, it adds a lot of noise close to the carrier. And the noise is a little bit unstable. And we can see all the way out here, there is unstable noise. And there is noise. If I switch off the oscillator by pulling the DC, you can see that the noise floor of the test system is far below the noise I see. So the bandpass filter is not very useful. I have changed parameters a little bit. That shouldn't make any difference. But now I'm going to test another crystal filter. This is a bit wider and has lower loss. Note that the S meter did not change much. I had set it to show 0 here, and now it shows minus 1.8 dB. But you can see here there is almost no noise. This filter does not add as much noise as the other does. Even here it attenuates. The bandwidth is 1.4 kHz. So this is something I can use to test the test systems. I disconnect the power supply to see if there is anything at all. And as you can see, none of the noise from the oscillator comes through. Here is the amplitude noise. Now that I have a big capacitor inside the box to remove audio frequency on the power supply line. At 10 kHz, that's here, I see minus 180. And at 10 kHz here, I see 10 kHz minus 177.4. And at 1 kHz, minus 168.7, and 1 kHz here, minus 171. So maybe there are contributions from the test system with the PN2060. I will investigate there by adding the filter. But first I will look at the phase noise. 100 Hz, that's a little bit outside what I can read here, but I guess minus 160. At 100 Hz, minus 159 or so, minus 160. So the agreement is reasonable, but maybe there is a little bit higher noise here. And I will look at that later. First I will check the phase noise. In Linrad I just click on the boxes. Here I see the correlation between phase and amplitude noise. You can see the traces. The amplitude noise is much higher than the phase noise. And here is the phase noise. And it looks odd. Means the phase noise looks lowest at about 1 kHz, and then it increases as the frequency separation increases. This doesn't seem right. I will look for the phase noise with the PN2060. So I stop, press phase noise and apply, and then start. And this doesn't look right. Stop. Okay. Well, something went wrong and I have restarted the PN2060 and I will have to wait for a while. But I can see very quickly that the noise is at minus 177 at 100 kilohertz. And it looks flat. And if I look at Linrad, it says out here at 5 kilohertz minus 177. But it goes lower. At 1 kilohertz it looks like minus 182 or so. And when looking here, it looks like it drops closer to the carrier. This is a little bit odd. I will wait for quite some time to get the proper statistics of the PN2060. Here is phase noise after a long time, and I clearly see there is a minimum at 1 kilohertz in the PN2060 as well as in Linrad. And the value I read is minus 180. And it's the same here. Whether this is noise from my amplifier or whether it is something in my setup, because I'm sending the same signals into Linrad as well as the PN2060. I will insert that filter I have to see whether this noise goes down, because then I would know it comes from my setup, otherwise it is from the oscillator. This does not look right at all, and I see best in Linrad. Here the trace is blue, which means that the correlation has negative sign. And the PN2060, I don't know what to say about that, but it shouldn't show like this when the correlation is negative, I think. Anyway, the output impedance of the filter is not 50 ohm outside the passband, so I will insert a 6 dB attenuator to make the impedance more like 50 ohms. So now I have a 6 dB attenuator after the filter. And this is what I see. And compare with what I had without that attenuator. It's obvious I had negative noise here, and now the level is lower and more negative than positive, but there are still yellow traces here. The reason is I'm below the thermal noise, and then measurements become inaccurate if there is an impedance mismatch. This is well known, and before trying to look at the noise far from the carrier, I need to increase the signal level. Impedance matching in the whole analysis bandwidth is a critical issue. Subthermally limited oscillators make use of a narrowband reactive filter at the output, which exploits impedance mismatch in the stop band to deliver the lowest noise floor. However, such filter results in anti-correlated noise due to the thermal energy in the power splitter at the instrument input. So this is well known, and it comes from this paper by Yannick Gruson, Adrian Ross, Ulrich L. Rode, Alexander Roth and Enrico Rubiola. Open access, and the site is here. The current signal level is 11.5 dBm. I have added the last stage, a noiseless feedback amplifier with 4 BF240 in parallel. It gives an output impedance of 50 ohms, and this inductor is to fine-tune the imaginary part, and the number of turns here set the real part. The power level now is 19.5 dBm. So now, with the final amplifier connected, it seems I have lost about 5 dB on the noise floor at 1 kHz. This is what I had before. Whether this is real or an artifact of the measurement procedures, I don't know. I will try with this higher power level, adding attenuators until I see the sideband noise go up at wide separations. Here is what I see with 6 decibels of attenuation on the oscillator. And without attenuation it was like this. So I'd see no difference here, but there is a significant difference here. And I think this is noise in the attenuator. Phase noise produced by the resistors in it. But I am looking for the phenomena at the noise floor, at the wide noise floor, that I had in the paper by Rode and others. Here is the result with 12 decibels of attenuation, and I compare it to what I see without any attenuation. And it is very similar. So I will try with even more attenuation. Here the attenuation is 18 decibels. And this is what it looked like without any attenuator at all. And if you look here, the attenuator in use now seems to not be noisy. There are many different resistors in the variable attenuator I'm using. And looking in Linrad, here, there is a small difference, but not much. Now attenuation is 24 decibels. The signal level starts to be a little bit low. It is minus 4 dBm here now. It was plus 9 when I started. Here is the original, plus 9.2. So statistics starts to become not so good here. In Linrad, I can change the gain within the system. So here I have an amplitude margin of 7 decibels. And the old I haven't saved, but it was about 1 dB. And as you can see, now the noise floor has lifted just a little bit. And here it's hard to see, but well, questionable. Now I have 30 decibels of attenuation between the oscillator and my test system. And I still get essentially the same result as without any attenuator, which I had here. Differences are very small.
But the signal, as you can see here, input is minus 10 dBm, which means that the thermal noise, which is minus 174 dBm per hertz, is minus 164 below the carrier. Now, half of that is AM noise, so let's say minus 167. But I am measuring minus 175. That's 10 decibels lower. Because what I'm looking at is the excess noise. The attenuation is now 36 decibels. I still get nearly the same result as I had without any attenuator, which is this. The same, roughly. Although now the result is very noisy. And here you can see the little dots. They say that the result is unreliable. But in Linrad, you can see there is a small difference, about 2 decibels at 8 kilohertz. But not really any difference here. This is in sharp contrast to what one would expect with a professional instrument. I return to this paper. This is the experiment I have done. Device under test, attenuator, and a dual-channel phase noise analyzer. The big difference is that the attenuator and the power splitter have the same temperature in my setup. As a consequence, TO and TS are the same in my setup. And as to say here, equation 19 predicts that the correlation is going to be negative because the temperature inside the instrument is obviously higher than the attenuator and room temperature, T ambient. And figure 3 shows the results when measuring this Wenzel oscillator with the PN2060C. And here we can see the noise floor at 10 kilohertz varies very much. And that is with attenuations from 0 dB up to 27 dB. The noise floor they see go from minus 180 to minus 160. And without any attenuation it is this green trace. And then the lowest result is with 15 decibels of attenuation. And then with more attenuation the result shows worse and worse sidebands. Then they have a model to explain this, and they can compute the real noise floor from that model. And here is the result of the same oscillator with attenuation from 0 up to 15 decibels with another professional instrument, the K-Site E5052B. And the result is similar. They did not go all the way up to 27 dB. This is from 0 up to 15 decibels. Here is the result explaining what's going on. This is a hacked FSWP where they have changed the color when a part is negative. And this is what I saw with my system when using a filter that made the impedance far from 50 ohms on the oscillator. And here is my own finding of the same thing when I had that filter. You can see the blue
because I have a different color for negative correlations. Although in the PN2060 the color is the same, I think it would be a good idea to change that as a warning to the experimentalist that this experiment is wrong. According to this paper, there are two problems. One is the thermal energy that differs between the power splitter and the attenuator. And the other thing is there could be crosstalk inside the unit between the channels. And there is a third problem they don't point out, and that is there could be correlated noise between the reference oscillators from power supplies or some other undesired mechanism.
Here is the setup for the measurements I just made. Device under test, stepped attenuator, hybrid, and then the signal is split in two legs, and each one starts with a stepped attenuator, low noise amplifier, and a coupler, and I had 1.6 and 1.8 dB, so I used them, and here the signal is coupled out to the PN2060C. Previously it was for the SDR IP units, and the signal going straight through has a position where I insert an attenuator as required between 0 and 20 decibels. And then there is a buffer amplifier, and this is to isolate for LO signals coming backwards from the direct conversion receiver. And these attenuators help for that when the signal is strong. And the reference oscillators are like this. There is a rubidium source to start with, and a hybrid splits the signal into two different PLL systems that control two local oscillators for channel 2 and channel 1, buffer amplifier, and a coupler from which there is a signal that goes to the PN2060, or previously the SDR IP units. And then there is a 20 dB coupler to send a weak signal back to the PLL. And then the strong signal comes to the direct conversion receiver for 1 and 2 channels. I have combined the crystal filter with some other boxes and cable to make a very good oscillator with respect to the sideband noise at 8 kHz offset. And here is the impedance. I have magnified the Schmidt diagram, but you can see the impedance is 48.7 ohms at 10 MHz, 50.43 8 kHz below, and 50.46 8 kHz above these points here. And I can switch on the oscillator, and then I get this ugly pattern, but I try to set a narrower bandwidth, 15 Hz. Then I get a more reasonable pattern. I see this little circle at the center, and then close to the oscillation frequency the trace jumps around. In different ways. The power is 8 dBm. Here is the arrangement. The oscillator and the filter. The output impedance of the filter within the passband is 50 ohms, but outside the passband it is very high. So I want to load it outside the passband. To do that, I am using a notch at 10 MHz at the other end of a 0.25 wavelength cable, and then with a couple of attenuators to set the impedance level And that gives me about 25 ohms in this point. So I use a matchbox to bring it back to 50 ohms. This introduces some selectivity, so I'm limited to about plus minus 10 kilohertz for a very good matching. And then to make it better, I have added 6 decibels of attenuation. So I have 8 dBm output power, and that should be enough to find if there are any problems with crosstalk or something like that.
Here is what I see after more than 27 hours. In Linrad, 486,000 averages, and in PN2060 the number of averages varies with frequency band. Only 79 from 0.01 Hz to 0.1 Hz, but, I cannot count that. 800,000 here, 8 million, 80 million, 800 million averages. Well, we are in a region where it is the performance of the test system that determines what we see. The noise floor with a 8 dBm carrier is at minus 185 dBc per hertz, the single sideband noise floor. So that is 185 here. So Linrad shows that the noise is below the thermal noise floor by maybe 8 decibels or so, but several dots are blue, about the same number as are yellow, which means that this is only noise. So, I can do something to maybe see better. I can go over to linear frequency scale, like this. The averaging when making one pixel out of several is done on the complex numbers, and therefore the noise floor becomes even lower. So it is well below 190. And it's odd that something happens at this point. I don't know. Anyway, I think we can say that the system is perfectly okay down to minus 185 dBc per hertz. Even though that the distance from the uncorrelated spectra, they are here at minus 155, the worst one, and down to 185. Now, the PN2060, it looks a little bit odd here. I think this is the performance of the unit itself. With so many averages as it has, this is a kind of signal, and it comes probably from internal limitations within the unit. One thing I understand now when looking closer is that the points with circles that occur on many places, they mark that these values are negative. Rather than making a color between a negative and maybe a positive point that deviates, the negative points are marked with these circles. A little bit difficult to see, but looking closer, it's obvious. And here, an old measurement where I suggested these should have a different color. It is very clear now that these are negative values. And they are in this old measurement I made with the filter but without any impedance matching afterwards. And in Linrad you can see that the corresponding points are clearly blue and high above the noise floor set by the imaginary part. And it's the same here. The imaginary part, the gray, is far below the points marked with circles. The amplitude noise is similar. It's also well below 185, which is here, and it is mixed blue and white points. And if I compress the X scale here, you can see there are a little bit more blue than white, but they are well below 185. I have added one more crystal filter. The effective Q has increased from 1.15 million to 1.83 million. I test one more time. Well, 1.833. When I look for the phase, I find that the phase is about minus 16, well, minus 15 degrees at the center. The power level now is very low, minus 60, and I make it rather large. The biggest I can get with this defective instrument, it's 0 dBm. That will affect the phase slightly, and now the phase is a little bit on the other side of 0. But when I look at the amplitude, the gain, it is very low because it is limiting. So I press auto scale, and here you can see that the gain has dropped to 2.4, and it seems to have shifted slightly. And it's meaningless to look for Q now when there is compression. And I have returned to minus 60 dBm, and then I see that the peak is at the same place. So maybe there is a small warming on the crystal, and that is the reason for the changes I see. Here is what I see after about 40 minutes. What I had before with this oscillator with only one crystal filter is this. And best seen here. It seems I have lost about 1 decibel. And if I look here, it's the same. And I interpret this as the power in the second crystal filter is a little bit lower now. I tried to make it similar, but 1 decibel is maybe a little bit too little to be sure about. Anyway, the interesting thing is what happens at close separations. There I expect a 3 decibel improvement. And I will set parameters to see better at close range. But before that I can see what I have now. It is minus 123 at 1 Hertz here. And before it was minus 121. But statistics is not so good, and I'm not quite sure that the noise floor of the PN2060 is low enough at this point. So I will set different parameters so I can measure the close range noise floor with Linrad. Here is what I see in Linrad after 17.5 hours. There have been some glitches, one here and one here, and there may have been some more that I cannot see anymore. I don't know whether that has affected the result or not. And here is what I see with the PN2060, and it's interesting to note that the result is very much the same. Here it says 90.6, and here, well, I cannot read decimals, but it says 90. 1 Hertz, 125, 124.8. Now, at 1 Hertz, I had 122 when I had a single crystal, because I lost 1 dB when pushing down the wide noise floor, which is now at minus 174, from 1 kilohertz and upwards. At 10 Hz I see minus 152.8, and that would be here. Linrad suggests it should be a little bit lower, but the noise I saw in this range between 10 and 100 Hz or a little bit above, that the PN2060 had excess noise here. This seems to have been fixed now. This could be because I have carefully grounded the screen of the USB cable here and connected to the ground of the coaxial cables going into the PN2060C. I have set the linear scale and expanded the vertical to 0.2 dB per division. And then I look at 0.1 Hz, that's here. And then I can read 90.3 to compare with 0.1 Hz, 90.6. And that must be well within the measurement accuracy for these two measurements combined. At 1 Hz the curve is a little bit noisier, but with 0.2 Hz per division I can read minus 125.2 if I place the mouse there and then check with the ruler that it really looks like, it could be 0.1 dB up or down. That's what I would guess from the curve. And here I see 124.8. And you can see the noisiness of the signal here. It looks like there is a noise peak where the red mark is and maybe 2 or 3 tenths of a decibel. So I am very satisfied that there seems to be no obvious error in one or the other software for these hardwares. And then 10 Hz, that is difficult in Linrad. The noise level is too high. I can read here minus 152. But at 10 Hz, this is too noisy. But it is below minus 154. And the PN2060, it sits on a little noise peak, and it says minus 152.9. So it's still reasonable. 100 Hz, it says minus 168.2, but here are these many spurs, but I have set higher resolution, a larger Fourier transform size than I had before. Now it's 1024, so the peaks are not so wide as they were. And it seems that the flat floor between these spurs is something like 2 decibels lower. So that would be minus 170. And I can compress the X scale in Linrad, so I get 100 Hz here. The spurs are much sharper here than in the PN2060, but the noise floor is above 170, but it is within the range of the imaginary part. Simply the performance of my direct conversion receiver is not good enough to see what the noise floor might be at 100 Hz. What the noise might be at 0.01 Hz, I don't know. Statistics is not good enough. This is a negative point, and there are many negative points in this region. I would have to wait several days to get a reliable value here. But it is below minus 40 dBc per hertz. I have got stability problems. It started here, and I have made bangs on the box with some tool. And here, well, it's more noisy, and suddenly it became much more noisy. And I will try to find out what is the cause of this. Probably it is in the added extra crystal filter. I have resoldered all the soldering points in the added crystal filter, or most of them, and restarted. And there has been one single event here. I don't know what that is, but maybe the problem is not solved. I will allow this to run for a long time to see whether it comes back. Anyway, at the moment it looks okay. At 1 Hertz I see minus 126.5 on the PN2060, and on Linrad at 1 Hertz I see minus 125. Linrad has not been running for quite as long time as the PN2060. At 0.1 Hertz, that's here, I see 91.5, and here I see 93.5. So with time, I would expect both of them to show the same. The amplitude noise is much lower than the phase noise. At 1 Hertz, it is below minus 138, because the imaginary part is up here and all the way down here, and the real part, the white, is in the middle of the dots for the imaginary part. And at 0.1 Hertz, it is below minus 126 or so. Now, after nearly 12 hours, I can still see some problems with the oscillator. These glitches here, maybe here, and this one that I already saw. But despite these problems, the phase noise I see with PN2060 at 1 Hertz is minus 125.7. And when I look at Linrad at 1 Hertz, I see minus 126, but this is a little bit uncertain. 125.7 might be perfectly correct. And at 0.1 Hertz, I see 92, while I see minus 94 with the PN2060. I will allow this to run some more time to see what happens with the glitches and if the results that I see differ much. Now, after 14 hours, there has been one very strong event here, and that has destroyed the performance as recorded by the PN2060. At 1 Hertz it is now minus 112.8, and that's really not good at all. Looking at Linrad, at 1 Hertz I see minus 126. That's because Linrad has an algorithm that detects single very strong events and does not include those into the summation of correlation averages. Something is really bad with the stability of this oscillator. The nature of the problem will be more obvious if I change the color scale of the waterfall. Something is changing the frequency by about 1 millimeter on the screen here. And then it goes up and down several times, and then suddenly it goes back into normal operation. And finding what is the cause of this is going to be very difficult, because operating the unit with the lid open gives noise due to the infrasound that is always present. The problem should be better visible in the frequency versus time graph, which I have in coherent mode 3. It's this thing. 1 point every 5 seconds, and the step size is 0.2 millihertz per division. So I wait and see. The frequency drift is very large with this scale, so I make it a little bit less sensitive, 0.05, and then I wait again. 2.5 hours, no problem has happened yet. I can see that from the PN2060 it shows minus 125.8 at 1 Hertz, so that's fine. I can see that the stability over longer times is not very good. The frequency goes up and down by about 1 millihertz or maybe 2. If I look at the Allen deviation, which I have here, I can see at 1000 seconds it is about 10 to minus 10. So that's not particularly good. And that is obvious, of course, from the frequency versus time graph. Now my reference oscillators are stabilized with a rubidium source, so this is the frequency variation of my test oscillator. And I guess this is temperature, something like half an hour or 1 hour going up and down. And there is some periodicity, could have to do with the temperature regulating system of this house. Here I have touched the BNC connector at the output. It gives a fairly strong noise bursts, sideband noise, but there is no frequency change. So this is pure amplitude noise, and that's expected. I just wanted to check that the problem is not related to the BNC connector. Obviously, there are two different problems here. I can see this. It doesn't affect the frequency at all, and it doesn't affect the phase noise at 1 Hertz. It is now minus 126.0, and that's very good. So this is something with the amplitude. It could be something with the computer also. After all, there is a sound card. This is a Windows computer, so it may do unpleasant things that I'm not aware of. But here in this mode, there is no routine that removes jumps in the phase. So the oscillator has been running properly, and this is a defect somewhere in the system. It might be not in the oscillator. This event was about half an hour ago, 1903, now 1933, and a couple of minutes more. And this is more than 2 hours. So it should be somewhere around here, and there is nothing. Here I have caught one event. The frequency has dropped by about 8 millihertz, and there is some structure in it, and the frequency is coming back gradually. And of course, when I look at the PN2060, the phase noise at 1 Hertz is now minus 113.6. So this is what I have to look for. Now that I know about that, maybe it will be possible for me to find it also with the box open. When removing the screws holding the lid to the box, I am causing vibrations, so I get a lot of noise. And the frequency has changed, and now it will drift away because the temperature inside is going to change. So, but at this scale it will be possible to see this type of abrupt frequency changes. So I will wait for it to stabilize to see whether the trace is flat enough so I can distinguish these things. I can see noise now, but it's weak compared to the interference problem I have. So this curve, the undulations on it, you can see that has to be the infrasound. The normal trace is like this. It is flat. But here we have undulations on the trace. The associated sideband noise at 1 Hertz is minus 113. So this is a 10 dB increase in the phase noise at 1 Hertz. I guess it will take at least half an hour to get a stable temperature again. Now the frequency is stable enough. I will change the scale so I will see those 8 millihertz jumps easily, like that. And then I click on the star to place the frequency at the center. And here we can see the variation of the frequency because of infrasound, and it's much smaller than the problem I'm looking for. I have a plastic straw, this thing. They are forbidden now in our country, but it is a very good thing to use to try to touch the various components in the box gently. As it turns out, this trimmer capacitor is very sensitive, far more sensitive than this one. It has a new position now compared to when I was running with only one crystal filter. After I touch that capacitor gently, the frequency is out of scale. I have to change the scale now. Seems I have to rotate that trimmer several turns to see if it becomes less sensitive. I have rotated it many turns. That didn't help, it was still very sensitive. But now I have turned it so the other side of the capacitor is doing the work. And now it is far more stable. And actually it was on this side I had it when it was running with the single filter. I have put the lid back to get rid of the infrasound. Now I have to wait for the temperature to become stable again. I had the x-axis running much faster when doing these experiments with the plastic straw. But now I'm back with 5 seconds per point. And I can see immediately that phase noise, it says minus 121 for the first measurement. So it's going to be okay. And maybe there will be no frequency jumps anymore. Or there could be some more problem. I don't know yet. There is still a problem here. This is when I arrived in the room, but this is something spontaneous that happened. I have modified the trimmers. There is no moving contact anymore. And the same here. There are still problems, as you can see. This happened 9:32. It is now 11:35, so it is 2 hours ago. 2 hours, it is somewhere here. And I don't see any problem here. So this is a different phenomenon from that was so bad before. It could be a problem in the two-channel receiver, because when I look in the PN2060, I see minus 124. Well, it seems it is affected also. The reason I don't see anything here could be that this graph is very slow. I had set it to 15 minutes for each point, because I have been sleeping. I went to bed just before 8 o'clock. So I don't know what this is. I have set a much faster frequency versus time. As you can see, it's really moving here. Half a second for each point. And I also increased the gain significantly, as you can see on the old. And maybe, if I am lucky to be in place when the next time there is a problem, I might see something. There are still some modest problems. I have used the application Velocity Lapse to make a slow motion video. And I caught an event, and I will demonstrate it here. You can see one has already passed, but here is another with the opposite sign. There is a frequency jump of 0.4 millihertz, so it's much smaller than what I have seen before. But there is a big event on the waterfall. You can see here, this is the noise from the mirror image, which is here about. So this means that I or Q has failed, and in channel 1, because channel 2 doesn't have any frequency jump. So probably a BNC connector problem. I have connected and disconnected several things several times. So I will look whether there is one that is unstable and maybe clean a lot of contactors for the channel 1. The oscillator maybe, or the signal, I don't know. The frequency jump is only in the green trace, means channel 1, and it is only 0.2 millihertz. But there is a big change in the waterfall. The white you have here at the frequency 0 means there is a large low frequency pulse. I have very big capacitors to couple to the ADC chip. And inside that chip there is something that suppresses the DC voltage. And here, that is sidebands from the mirror image, which means that the amplitude change is only in I or in Q in channel 1. So there is probably a connector problem near the mixer in channel 1, I or Q. I am repeating the measurement with the same signal to all 4 inputs of the PN2060C. Now that I have the screen of the USB cable connected to the screens of the input signals. I'm using the signal of my new dual crystal filter oscillator and run it through this filter, which is an extremely good suppressor of overtones, and then through an attenuator into the PN2060C, all 4 inputs. The PN2060 has been running for over 18 hours now. Statistics is very good. You can see the very smooth signal here. This is noise and here is noise. You can see the difference between the green trace and the light gray. It's essentially zero. Means the imaginary part and the real part have the same level. But here, this is a distinct signal, and you see the circles everywhere, means that this is negative. So this is correlation with the wrong sign. So it's some kind of crosstalk inside the box. It couldn't be external. So I don't know what it means, but I can say that the level is very low. But when the oscillator is approaching this level, there are artifacts. If the signal is present also when there are different signals at the different inputs. I will look at this sometime in the future, but right now I can see that this does have some effect on what I'm observing. The negative signal is at 10 Hertz at minus 155, and I have seen minus 152 or that order when measuring on the oscillator, and that cannot be correct because this thing is subtracted, so performance of my oscillator is not as good as minus 152. It's a little bit higher, and I don't want to take the trouble to compute that, but I have to be observant on this phenomenon. Here is the setup I have used to optimize the oscillator. This is a slow motion video. I have stopped it just when it starts, and you can see the PN2060C here and Linrad here. And for example, look at the what happens at 1 Hertz. It is this point, and you can see the value here. It is minus 145.7 at this point. In Linrad, you can see here at 1 Hertz, it is where the mouse is. The value is minus 133, and it's obvious this is very unstable because the signal is very noisy. But when I start the video, you can see how it converges and how this one also jumps up and down and converges at some point. And you can see here the numbers, they are the average of all the decibel values over the green range, which starts here at 0.7 Hertz and goes up to 3.5 Hertz. So it's the average of all the yellow points, and there will be no blue points when enough data is collected. So I start running this thing. And you can see this goes towards minus 125 or 26. And this goes to minus 126. And the average, which is the same we have to the left, you can see here also, it is now minus 134.77. And here it stopped. By allowing this to run for about 1 hour or maybe 2 hours, I get the average phase noise with a precision that is better than 0.1 dB. So I can see the effect of small adjustments. And the purpose is to tune the two filters so they work together in the optimum fashion. And also the coupling and the level within each one of them. Unfortunately, my oscillator suddenly became very noisy, so I'm not going to use this. I have to look for what the error might be. But this is a tool and I wanted to show what it's doing. The phase noise is very strong now. As you can see, something like 86 dBc per hertz. The problem seems to be located in the first crystal filter. So I touch components there to see where the sensitivity is worst. I have found the worst problem. I had used this kind of foam plastic for thermal isolation on the little thermostat that I have the crystals in. And this material was in contact with the wires from the crystals. And obviously it has been moving now and then, creating these horrible noise bursts. Now, that's not the only problem. I have one more, or maybe several more problems. You can see the glitches that have come here, and here is noise. That must be another phenomenon. Anyway, now I am recording the raw data. You might see the blinking S up here. So I can look in detail what these glitches are, but I will leave this thing running for quite some more time. It's now 16 hours. It will run until tomorrow at least. Anyway, the performance I can see when this data is included is with the PN2060 minus 124.1, and in Linrad I see minus 124.6. So they agree on the performance, and these noise bursts are more or less included in that PN2060 certainly. In Linrad, maybe some of this data has been excluded because of too much noise. But one thing is clear. The noise burst you can see here, that was when I put the camera on the table. Many hours have passed without any errors, but now suddenly, 9:30 or even earlier, 8, there have been instabilities, not only these strong events, but also these little weaker. I will look at it, but before that I will try to change the temperature to see whether that is causing these things. So I will blow cool air and, room temperature air to cool it, and then hot air to warm it to see whether something happens. When I was warming the unit, there was a big problem, but after I moved away the warming equipment, there was an increased noise level here and also here. I now do the cooling operation again, like this. Just air temperature, room temperature for about 1 minute. I was very careful not to touch anything to induce vibrations in the box or on the table. But there is a dramatic effect of this gentle cooling. You can see here is some event, and I can see also here that the noise floor goes up sometimes. When the trace is the same on the green and the red trace, that means that the dominant noise is from the device under test and not from the channel. Like here. And also here it is a similar trace, red and green. That means it comes in both channels, so it is from the device under test. It's obvious 1 minute of gentle cooling here has caused more than 10 minutes of noisy operation. So the problems I have seen are related to temperature, and I don't know what kind of problem it really is, if there is a component that behaves badly, or if it is mechanical strain in the wires and other stuff that releases or moves things when the temperature changes. I will analyze the recorded file. It is still recording, as you can see here, and it has been running for now 32 hours. So I will pick the interesting times and see a little bit more what is the nature of the instability. Here I am playing that long time recording and have started now close to the first series of events. And I am repeating the recording over and over again from 11:10 until 11:46, that is 36 minutes. And here you can see the big thing. That is when the recording is started again at 11:10. And I can run much faster by pressing F3. And you can see the recording started. Oops, look here. Big amplitude jumps in channel 1, but the frequency is not affected. So this is the channel 1 and not close to the oscillator. Here I am running in normal mode. And here we have these things, and I see nothing on the S-meter. So I have to change parameters to make it more sensitive. Here I can see very clearly the big transient. That is when the recording starts again at 11:10. And then we have these little jumps in amplitude on channel 1, while channel 2 doesn't have those. And then here is a big transient, and in channel 2 maybe a little jump here at the same time, but I'm not so sure that is significant. Anyway, this is my channel 1, it's not my device under test. And here we have this glitch. And again, a problem in the amplitude of channel 1. And I could see it is in either I or Q, because the amplitude went up in the mirror image frequency also. As you can see here. The next series of events was starting at 8 o'clock. And this is very strong in the I, but weak in the Q. And here is the other way around. So this could be something different. And it looks perhaps that there is a little more noise surrounding the carrier. Now I have a problem. If I want to look at this from 7:55 to something, that is more than 24 hours. So I should put 24 plus 7, that is 33.5, if I compute correctly in my head. Start at 33.5.0, and I didn't think about that when I wrote this code. I have to change something in the software. Well, now I want 32.40.0 to 33.40.0. That's from 8 to 9 in the morning. And if you look here, you see the typical problem of amplitude jumping up and down in channel 1, but the frequency looks quite okay. And here the recording starts again, this 1 hour. Now I'm looking from 11:45 to, well, a bit forward. And you see here, suddenly there is a big frequency jump in my oscillator. So this is the device under test that made something. And here the recording starts once again. And if you look in the baseband graph, it looks very similar, but it's all over the place. And it's a big frequency jump. But there was also something in channel 1. Now I am starting the last 3 hours from here where the mouse is, and it is this whereas the point of starting. Then the time was 12:35, and here was the first sequence of problems. That's when I was cooling, moving some sheet of paper. This structure here is not clearly visible in the frequency versus time, because the scale is so compressed in order to see this big jump. And here something irregular happens, a small jump, and it drifts a little bit steeper. And here I was warming. Well, the 3 hours had elapsed. So I'm not sure exactly what I was doing, but I was changing the temperature, and that is affecting the test oscillator very much. This dust cleaner, it contains cyclopentane and can be used to blow away dust. But it can also be used to apply some cooling on this box locally. So I tried the trimmer capacitor on the first filter and give it a short blow like this. And then I look at the computer screen. I have set a faster waterfall in the baseband graph. And then, as you can see, something happens because of this short blow locally. And I didn't touch the box, and I didn't make any significant vibrations on the table. Now I do the same on the second tuning capacitor. And this was obviously much more sensitive. I tried this once again. Now the cyclopentane is a little bit cooler because I have evaporated a little bit of it. And again, the effect of cooling is quite strong, but it doesn't give long-lasting noise as I had expected. So it could be the vibrations of the moving air rather than that I changed the temperature of the capacitor. Well, it's only a short interference I get. I don't get into the noisy condition. At this point in time, here, I cooled the larger surface, and that brought the box into the noisy condition. Well, I will wait for a while. Well, that really lasts for a long time, I have found what half of the box contains a problem. The instability has lasted for about 10 minutes, but now it has calmed down. I take a small chunk of snow or ice from the freezer, like this, and place it somewhere on the box. That was very little, and it has already almost melted. That didn't make much change. It was at this time. So I drop some ice at a different spot, like that. That really had much more influence on the noise situation. But the noisy condition doesn't last. So this may be just because of the vibrations of dropping that little piece of ice. At this point in time, I placed a small piece of ice very close to the tuning capacitor of the second crystal filter, and it had a long-lasting effect. Here, some ice very close to the tuning capacitor of the first crystal filter. It had an effect, but it didn't last. Here, the PCB right between the two tuning capacitors, and that gave a significant effect for a long time. And now I dropped close to that point, but right above the thermostat oven. And that seems to be similar in effect. I have to wait for a while to see how it develops. I had a suspicion that the foam plastic that is around the thermostat oven would be the problem, but this seems to be not as bad as this. Now the unit is in its noisy state. I will heat the most sensitive region, which seems to be about here. On the other side is the amplifier of the first crystal filter. So I put the soldering iron there for a while. Long enough to make the tin float out significantly here. As expected, the oscillator is now very noisy, or it was while I was heating. We'll see what happens next. Recovery is rather slow. It started with an average noise of about 125. That was after 57 averages. I restarted and it turned out to be 128. Now it says minus 130, but normal would be minus 133.5 or something. So something is misbehaving and calms down. I don't know what this could be. I can try with the mechanical vibrations. The universal tool. Bang once. And it gives a wideband pulse, of course. As you can see here, perhaps, there was a small frequency shift. You cannot see it here, but this is the second harmonic, so the shift is twice as big. And it's about 1 millimeter on the screen here. Performance is back to normal now. It says minus 134 down here. $134.5. I have slowed down the baseband waterfall by a factor of 10, so now it says 20 here. And then I will see tomorrow, because now it is late in the evening. The oscillator has been running for 20 hours now without any glitches. You can see now and then the frequency has moved a bit from here to here. That's because there is an AFC in the software that moves the carrier to sit in the center or close to the center of this filter. I'm using the signal that passes through that filter for an IQ demodulator to get AM and FM. That's the way I'm detecting the signal in Linrad. The performance according to the PN2060 here is minus 124.3 dBc per hertz at 1 hertz. That's not quite optimum. I have seen minus 126 a couple of times. Maybe I'm not running the proper power level in the crystals now. In Linrad, it's hard to read. It looks like minus 125 here. I can change the scales to see better. It looks like minus 125.0 when I look with the log scale like this.
This is the foam plastic that I was using as thermal isolation for the thermostat oven. And it has deformed a bit, but essentially kept its properties. I think maybe this material is moving a little bit, creeping, or what you could call it, causing these micro vibrations that harm the oscillator performance. I have replaced it with cotton, just plain cotton. I have added small capacitors to the tuning capacitors for the crystal filters. That is to make the capacitance small of the tuning capacitors when they are tuned for the correct frequency. The idea is that the current through the sliding contact should be very small, because the sliding contact might have a noisy contact resistance. Then I have tuned the oscillator for a frequency very close to 10 MHz. Now it is 75 millihertz below 10 MHz. And I have also added a capacitance diode, so I can tune the frequency electrically. So now the oscillator is ready to be used as the channel 1 reference oscillator. The performance I see now is minus 124.0 at 1 hertz here, and minus 151.2 at 10 hertz. And that is significantly better than the current channel 1 oscillator. Here is Allan deviation, correlation mode 3 in Linrad. And you can see the green dots is the result, the Allan deviation with reference oscillator in channel 1 and my Wenzel oscillator. The red dots is my reference oscillator number 2, also of course with the Wenzel oscillator. And you can see some differences. The green curve starts to go down here. It crosses the red here, because the time constant is much faster for the channel 1 oscillator when it's locking to the rubidium reference that I have also as a locking for channel 2. If I would wait long enough, both channels would coincide. The yellow trace is the correlation between these two, and it is a little bit below, but at very long times the number of data points is too small. The correlation becomes negative for the last point.
Here is more interesting, that is frequency as a function of time. And the green trace looks a little bit more noisy, not really much more noisy. But the correlated stuff here, that is the Wenzel oscillator. And the general appearance of this curve is reasonably flat. I will save this. That is in Linrad. G for GIF file. I have been running the PN2060 at the same time. And the frequency is 12.9 Hertz above 10 megahertz. That's because best performance from the Wenzel is with the frequency adjustment screw to its clockwise endpoint. And that is not exactly 10 megahertz. At 1 Hertz offset, 120.8 dBc per Hertz. That's very good. 10 Hertz minus 147. Now I'm using the new oscillator for channel 2. It has not locked yet. It is drifting, as you can see. And the error seems like about half a millihertz. And I can check with this PN2060. It says 2.6 millihertz, 3.1 millihertz. It's a difference of 0.1. And channel 1 is a little bit below channel 2. Now the time constant for the PLL for channel 1 is set to minimum. So I expect to see the noise from the rubidium oscillator in channel 1 pretty soon when it has locked. This is far from what I expected. Previously I had this, and now a very strongly correlated signal. This means that the Wenzel oscillator behaves badly now. I don't know the reason. Maybe it is something with the power supply. I will try another one. I have changed from this one to this one, set for the same voltage. And I have changed the vertical scale by a large factor. You can see how it comes back reasonably close. Now the vertical scale is the same as what I had before, with this result. So the power supply failed at this moment. It was okay very recently. Well, I have waited for a while, and we can see that the noise of channel 1 and channel 2 looks very similar. But in the previous screen there was a big difference between channel 1 and channel 2, and given the long time constant it lasted for a while, and it explains why channel 1 is a much higher Allan deviation than channel 2. I will make the sweep the horizontal time step. It is 1 second now. I will change that for 10 seconds and then restart to get a better picture whether that big difference that was for channel 1, if it will come back now and then, or if it was just once in a long time. Well, there are problems in channel 1. The 2 crystal oscillator, which we can see here and also here. It seems not to affect the frequency, however. If I look here. Allen deviation at 10 seconds is 1.35 and 2.03 times 10 to the minus 12th respectively. That is a factor 1.5. I think one should take the square of it to get it in decibels. That means 3 decibels better at 10 Hertz. But at longer times it looks differently. And that is better to look at the frequency versus time. It looks like this, and it seems that the green traves has a little bit less noisy for short times. That's the 10 Hertz offset thing. But at longer times, several hundred seconds, the green trace is more noisy. And that is a bit unfair because the time constant in the PLL is much faster for the green trace. I will set the same time constant to see what happens then. Well, there is an instability, a significant problem. Means that I think this oscillator is not useful for the purpose. It is, however, better at 10 seconds. Here is the previous result. And you can see the red dots. That is channel 2. It has improved significantly because of a better power supply. But channel 1 is significantly better than channel 2 at 10 seconds. But here at maybe 50 seconds, the curves cross and the green dots go straight up like that, corresponding to these large frequency variations. Like the previous oscillator, I could of course set the fast time constant, but there are these instabilities you can see here, and they are in the amplitude. So I think this will be enough with this experiment. I don't want to pursue it because I have other ideas to apply what I have learned from this experiment. There are several things that I will do in a new experiment. Despite the instability at long times, the sideband noise is significantly improved at 0.05 Hertz or 0.1 Hertz. You can see now that channel 1 is better than channel 2, and it was worse by 5 dB or something before. But I don't think this is really worth the loss of measuring Allen variation over longer times.